There's a couple of basics here that you need to know about electric charge. There's two types of electric charge. We define them as negative and positive. So we have electrons basically are the source of negative charge, and your protons are positive charge. Okay, so we have that. Now, the base unit, the smallest amount of charge that there is in the universe, seems to be 1.6 times 10 to the negative 19 coulombs. We measure charge in coulombs, so each electron has got that charge, and so does each proton have that charge. And the only difference is that the one seems to be negative and the one seems to be positive. And they decided, just like they decided to call the right hand or the right side, and the left side, they decided to call the one positive and the one negative. And yeah. Yes, it takes up, but it's they will make up a one basic unit of charge, but that's true. You do get subatomic particles relating to charge. Okay, now the idea with the law of conservation of charge is that charge we feel. Now this is not totally true, but generally that charge can either be destroyed or created, but it is conserved. So you get charge flows. Now, this doesn't always happen in for instance, you can get the making of charge, but when you make charge, if you make a positive particle, you'll always have to correspondingly make a negative particle so that you get conservation of charge. So the total amount of charge in the universe seems to be constant. If you make a negative charge, you also make a corresponding positive charge. We'll see that in the nuclear physics when we do that. Describe and explain different electrical properties of conductors and insulators. Basically, a conductor allows the flow of charge, the flow of electrons, where insulators don't. Now, there's quite a lot of information in the PowerPoint. Now, I would like you to go there. I'm not going to go through all of this. This is some reading that you can go through. There's a whole thing about what a conductor is and what an insulator is, and so forth. This is looking at the sort of conservation of charge, going down here, what I've just been talking about. So there's a lot of information here in the PowerPoint if you can use that. Okay. Now, here's a conductor. These are usually metals. Basically, with metals, you get the valence electrons, or the electrons on the outside part of the atom, are relatively free to move about within the structure, and so those are the particles that move within the conductor, and those are the things that conduct the charge, and they can be used in wires and so forth to do that. Alright, insulators, same thing. And I just want to find here my Coulomb's law. So this is an important law. Going here, state Coulomb's law. This is the law here. The force between 2 point charges is directly proportional to the product of the charges, and inversely proportional to the distance apart squared. So it's a very similar law to Newton's law of universal gravitation. It's got that same format of it. If I bring my data booklet back here, it's there in the PowerPoint so that you can get that. When I bring this one over here, there we are, you can see both now. This is Coulomb's law. You see the force between two charged particles is equal to the product, or is proportional to the product of the two charges, and inversely proportional to the square of the distance between them. So you can see there is a great similarity between these two. Okay. Alright, so there's this formula over here. Now, again, we have a constant of proportionality, this K, and that K, constant of proportionality is K, and that K, when we look at it, it's quite interesting to see the size of that K. It's given here in our data booklet, again. It's this one over here, the Coulomb's constant. Yes, now there's two K's. There's Stefan Boltzmann's constant. The Boltzmann's constant, we'll look at that at another stage. But here we're looking at Coulomb's constant, which is K. And it's this one over here. It's about 9 times 10 to the 9. Remember we had G, which was 6.7 times 10 to the negative 11. Now, they are very closely related. It's just the difference here that you've got kilograms and you've got coulombs. So mass is the stuff of gravitational force, the amount of mass there is. Charge, that's also stuff, all right? The amount of charge that you've got. We call that charge, and it's measured in coulombs. Now, as you can see, this one is much greater. This is 10 to the 9. This is 10 to the negative 11. You've got an order of magnitude of something like 10 to the 20 difference between the two. Your electric force, your force due to charges, is hugely more greater than your force due to gravity. This is one of the fundamental things that physicists are struggling to understand when they're trying to unify the different forces. They find this gravitation very difficult to unify because it's just so small. It's very difficult to understand. So this is your Coulomb's constant. This is what you're going to need. The Q is the charge. That's the unit for coulombs. Sorry? Small c. Small c can be different things, like can be the speed of light and so forth. But your big, this over here, this Q, is the charge. It's measured in coulombs, and the unit for it is a C. All right? Okay. So it's a product of the charges divided by the radius is measured obviously in meters. The force is in newtons. Okay. Now, just as you get a gravitational field strength, you also get an electric field strength. All right, electric field strength, and that is the force per unit charge at a specific point. So this E here is your electric field strength. All right, that's your electric field strength, and that's the force per unit charge. So again, if I have one charge over here, say call it Q1, and if I have another charge over here, Q2, there will be a force between them, certain distance between them. These are points charges, let's say that is R. Now, there will be a force acting on Q2, and that force will be depending on the signs of the charge. If this is negative, if that's a negative charge and that's a positive charge, there'll be a force of attraction between the two. So you have a force, and that force will equal K Q1 Q2 divided by R squared. Now, the electric field strength, the E, would equal K Q1 Q2 over R squared. And if we were looking at the electric field strength at that point over there, if we were looking at over there, let's say looking at A, so the E, the electric field strength at A, I'd have to divide by Q2. So my Q2 would cancel, and I would get K Q1 over R squared. All right. Okay, but it is Q1, but we cancel out the Q2 because it's yeah, that's right. Q1 is left because we're looking at the force that Q2 experiences due to Q1. All right, so it's the electric field strength at A, where Q2 is. It's the force per unit charge that it will experience due to Q1, and that's why up here. This is Q1, and this over here is Q2. So if we're looking at A, if this is A, at this point over here, there is an electric field strength. There's an electric field. If you put a particle there, it's going to be affected. It's going to be influenced by that Q1. The force per unit charge gives an idea of the strength of that field at that point. Q2 is not a zero. Because your definition of your electric field strength is the force per unit charge. So I'm dividing the force, which is that, dividing by the charge, and therefore the charge will cancel. One of the charges are going to cancel out. It all depends what you're looking at. If you're looking at what Q2 is experiencing, then you must cancel out Q2. If I was looking at over here, at say point B, and you're looking at the electric field strength of that Q1 experiences, then you divide by the Q1. So it all depends which one you're looking at. Now, finally, just to clarify one thing over here, we see we've got this formula over here. This formula over here. This formula is the same as that formula over there, except we have the K is equal to 1 over 4 pi epsilon 0. And this over here is the permittivity of free space. Alright, that's relating to the electric field. Now, that changes when you go from one material to the other. So if you were dealing with this in air or in a vacuum, you would use this over here. Or this value E0 is for free space for a vacuum. But sometimes you've got charged particles that are acting in materials, other materials like in oil and so forth. You'll get charged particles there. They will experience different forces because their E here, this E over here, this epsilon here would be different. The permittivity. Now that E0 is also given to us in our data booklet. So if I go back again to my one more, I go down here. There it is over here, E0, permittivity of free space. If I do that, if I have 4 pi times E0, putting this value for E0 in here, I get the answer I get for that is my K, is this one over here. So it's exactly the same formula, just written in a different way.